why the story about spin will be delivered. There are several reasons. First, if we are building fundamental education for all of you for next courses, you cannot be a competitive chemist without background on spin. A lot of you who do or will do wet chemistry experiment will characterize molecules with nuclear magnetic resonance, which is based on a nuclear spin. So concept is needed. In Schrödinger equation, like for hydrogen and heavier atoms, there are 4 quantum numbers. One of them is spin. And specifically for Spencer and Zane, for their projects, concept of spin is not literal part of your project, but a math developed in spin will be used for the interpretation and explanation of the projects by Zane and Spencer. The Monday lecture, if everything goes as I planned, will be the really interesting, strong, and on the sharp edge of the modern science. So we are building something minimal amount to do something competitive. Without spin, we cannot go to the Monday thing. Okay. So where I would like to arrive by the end of the meeting. The spin is like I'm going to say something that please do not reproduce in public. It's only a pedagogical concept. So if electron is a sphere of charge sphere, and it rotates around itself, then due to motion of this little sphere around itself, it develops an angular momentum. And if it rotates forward or backwards, the spin is oriented upward or downward. So it is just makes a connection with angular momentum. But such argument cannot be pronounced in public, especially among scientists, and maybe in general public as well. Because if one makes calculations in support of this idea, it will be achieved only if the circumference on the sphere moves forward with speed quicker than speed of light. So there will be some paradoxes. So it is analogous to angular momentum, but it's better to just accept it as is. So that it can be up or down. And so I'm going to tell where we should arrive if everything goes favorably. So in nuclear magnetic resonance experiment, when a molecule is placed in the very strong constant magnetic field, the spin of like nuclei molecule or starts to perform so-called precession. So instead of being oriented along magnetic field or counter magnetic field, there is a chance that it will make little notations, oscillations. And especially these oscillations can be facilitated by transversal magnetic field, which is not constant, but with some certain frequency. And if the frequency of this transversal field matches the natural period of rotations for spin that is determined by constant magnetic field, then it will facilitate these rotations. And then one can scan different frequencies and see the response. So there will be, I want to provide as much as possible or as less as possible math, so that we all here accept the idea that although spin can be only up and down in quantum numbers, it can be also treated as three-dimensional vector, and there are ways to make it to rotate. So if we approach the concept of rotating spin, I will be more than happy of today's meeting. And if you admit the connection between spin and magnetization, and you admit that it can be oriented along x, y, z, or just some mixed angle, then you're good. Make sense? Please ask any questions now, because when I start the slides, it will be really an attempt to be quick. Okay, Spencer. Hello, Spencer. Nice to see you connected. Share screen. Slides. So a little comment, and this comment was for everyone in previous years when majority of class attendees were doing different values of momentum in multiple runs. But this year we have very diverse projects. Kennedy is changing or will be changing strengths of electric field. Zane is changing offset of potential energy surfaces. And but for Connor, maybe it is applicable. For Spencer, maybe it is applicable. But for Jared, this diagram is most appropriate. So the idea is that there is an activation barrier for reaction. And the higher the temperature, the larger is probability that reaction will go over the barrier. Okay? So here is how one can see the project. So you select model, you have a potential, right? You can just measure how high the barrier is, and then you start actual work. You set up initial momentum, run dynamics, compute the rate, which means the slope, how quickly population goes from left to the right. Okay, and then you repeat it several times to accumulate rates as function of different values of momentum. And then one fits it into so-called Arrhenius law that I will mention at the beginning of Monday. Or you can find it, or you maybe know it from freshman chemistry. It's like a very basic thing. It's over here. So if one knows at least 2 points, or better, more points, of the rates as function of temperature, momentum is connected to temperature, then one can find activation energy. And then by comparing activation energy from Arrhenius law and from just visual evaluation of the height of the barrier, one finds and makes some conclusions. And it is not just a flavor of true science, it is something competitive that you can do for women. Okay. And here I just typed in this stuff in details. So, and here is the table for momentum, rate, and then later on it will go into the Arrhenius law. So I think I will come to the lab on the coming, there will be last lab number 12 on Wednesday, just to tie the loose ends. Although right now, most of us should have projects ready to go, and the major results are expected to be done before coming Wednesday. I will come into the lab and help to do last effort. And the analysis will be interesting if the kinetic energy bigger, smaller, or equal than activation energy. You'll see different regimes of modeling. So, spin. The table that I'm showing here will be one of the intermediate results. And if we are in the rush, there is no time to rewrite and report everything here. But the idea that I will come and prove that if we are considering spin, then instead of looking on its actual rotation, which is not a good thing to do, if you just accept it as a two eigenstates, two quantum numbers, we can process all phenomena related to spin in the algebraic space where there are just two discrete spaces. And in some sense, all our efforts during the class were bringing us to this point where one can do big science only in discrete space of eigenstates and expansion coefficients. So if there are two spin states, and typically the alpha and beta, in vector space it will be 1, 0, and 0, 1, right? Basis vectors. Then all states are expressed in these basis states, and operators that correspond to transitions between states will be either this set of matrices or this inverse cat and bra of different compositions of subspeeds. And this language, this dictionary, will enable us to speak about nuclear magnetic resonance, about Markov's theory, and about optical transitions. So it is one of the beautiful part of the physical chemistry and quantum theory that can be provided in a self-contained, absolutely logically consistent box, so to say. So if one does know the spin, and if there are like layers of metal atoms, each of which has its several electrons, several spins, they add together and sometimes they are not paired, then by multiplying the spin by constant, which is called magnetism, or one gets magnetization. Like in iron, in manganese, there are a lot of spins, and therefore they are magnets. And here is the last slide, which I would be very happy to arrive to. It's a challenge for me, but I'll try my best. So, if too many things, but I need to introduce several things before we arrive here. So, if one composes the specific operators out of this spin Bryant cats, one can correlate the state of the spin with direction of the magnetization in space. Although spin will have only two states, but since they are complex numbers, there is a chance to find more than two independent directions. Actually, three for our Cartesian space. And the projections of spin in x, y, and z directions expressed in the equation that I will introduce, upon placing the spin in the magnetic field, will perform rotation, very similar to expectation values of creation and annihilation operator, or position and momentum of harmonic oscillator. The projections of spin in x and y plane will rotate, one as cosine, another as sine. And and the frequency of this rotation will depend on energy offset of eigenstates of spin up and down, which in nuclear magnetic resonance is controlled by strengths of the parallel magnetic field. If one looks on these three numbers, and the z component will be constant. If one takes these three numbers parameterized by time, they will be a vector on a sphere. And if you perform equatorial rotations, so in nuclear magnetic resonance, magnetization in the experimental cell also goes performs rotations at radio frequency. Any objections? Okay, so if you arrive to this point, it will be really, really great. Whew. So angular momentum is radius times momentum. It goes transversal to the direction of rotation. Algebraically, it is cross product, and if one plugs in quantum operators of momentum, it will be like for z projection, it will be position and momentum of other two directions. Like, angular momentum in z direction depends on position and momentum in x and y. And then vice versa. If one practices multiplication of these pairs of operators, then there is a beautiful property. If our course would take, become one would take a year instead of half year, it would be definitely an exercise on this. But now we all are lucky not to do it. Or not lucky for not seeing the beauty of it. So same as we were making commutation of position and momentum, right? We were assuming that after operator we plug in an unknown function. So if we multiply angular momentum operators, we need to assume that we plug in function, then we practice differential operators, and if one carefully does it, one will obtain the result that this pair of rotations in x and y is equivalent to rotation in z. And if you ever were practicing engineering software to design models, or computational chemistry software to design molecules, or rotating objects in space, one can when drags and drop and changes the angle of three-dimensional object, one can notice that making little wiggling in one plane, one can induce rotation of the overall object in transverse direction. So angular momentum corresponds to rotation. Rotation a little bit along x, a little bit along y, and then rotating backwards is equivalent to rotation along another axis. Anyone is welcome to oppose it. If no, I'll go forward. And here is the shorthand notation. So Lx, comma, Ly, rectangular brackets, equals minus I Lz. So I'm going to bring some statements, maybe not as rigorous proof, but inviting you to believe that if instead of these operators of rotation of this rigid rotor, which can be like two diatomic molecule or electron rock nuclei, if I replace with Lx, Ly, and Lz with appropriate operators for spin, which is rotation of this pseudo object, they will follow the same commutation relations. So commutation relations for spin projections repeat commutation relations for angular momentum. Here is the stuff that I skipped completely from this class, but if you go over for graduate class, or if you need to exact equations for hydrogen atom, will come for these solutions. So that for rigid rotor, there is a dependence on two angles, and it can be factorized as dependence on angle, azimuthal angle that we have solved, right? Times the spherical function, which has two quantum numbers, and that I was showing as images, and you were seeing it in freshman chemistry, but we are skipping detailed analysis how to get it, because it's more advanced. Okay, so spin rotating forwards and backwards, state when it rotates forward, state when it rotates backwards, and any state of the spin can be a superposition of these two rotations. So it can simultaneously rotate forward and rotate backwards with some proportions. It's okay in quantum world. Now, we need to develop the mathematical technology to describe how the spin is fluid, right? To find Hamiltonian, to set up transitions between these spin states. And before we go forward with this, I admit that it is kind of a little counterintuitive, even after 3-4 months of physical chemistry. So I'm going to bring up this idea of these two quantum states and transition between them in the simplified pictorial way in a couple of slides. So here is the degeneracy for three-dimensional data, right? So what we were doing a couple of meetings ago. And here the value of magnetic quantum number takes integer values, right? So when there is no rotation, degeneracy is no degeneracy, 1. When it rotates with quantum number 1, amount of angular momentum is h bar, right? Then degeneracy is 3. So here is a crazy number. Is it possible to have a degeneracy 2?
No. Well,
it is not possible.
No, because you can only have.
If it is a rigid rotor, right? But the spin is a crazy concept that allows us to have a degeneracy 2. So if one assumes that it rotates forwards and backwards with half integer, then on this diagram you have 2 additional points. Here, plus 1/2, minus 1/2. And if I skip the empty cell, I'll put here angular momentum 1/2, degeneracy between 1 and 3, 2, and it will be kind of fitting the stuff. But all of those things are only pedagogical means. Do not speak it in the public. It's just a connection. The right things to say are just quantum number of the same dimension as angular momentum. Period. Okay. If we develop mathematical description, if we represent these quantum states as vectors, then there are 2 basis vectors, state 1 and state 2. Expansion coefficients can be complex. Now you can lean back and relax for about 10 slides, but I will skim through them very quickly. So 4 quantum numbers, rotating forwards and backwards. And here are alternative notations for this spin quantum number. Up and down, alpha and beta, arrow up, arrow down, 0 and 1, plus and minus. Different authors use different things. So there is no analogy of spin in macroscopic life. It's possible only for microscopic. But suppose a student or instructor can have different states, an all or lark, like getting up earlier or later, or irrelated to people. Suppose we have a mythical object, like an all. There is a wizard that can convert all into skylark. So birds are quantum states. Wizard is operator. It changes the quantum state. So we use cat vector of all and cat vector of skylark and the operator. Okay? Now, can we express the operator in terms of bra and ket vectors of the basis states?
Yes.
Yes, and I'm going to do it. And any of you in class or online, probably, I'm sure you could do it, just for the sake of time. So, if we have bra and ket of the all, and we do product, scalar product, it will be 1, because they are good quantum states, and they are orthogonal to each other, right? If we set bra and ket of the skylark, it is orthogonal to each other, it will give 1. Now, if we make an overlap of scalar product of an all and skylark, it will be 0 because they do not coincide. And if we swap the order, it still will be 0. Now, if we here for the scalar product, we were writing bra and ket. By multiplying bra and ket, we get 1 number. But if we swap and multiply ket by bra, it will get operator. So if we have ket times bra for all, it will be an operator that converts an all to the all. So like, if it will be a direct product of the skylark and all, it will convert an all into skylark. So if we set up a wizard in this form, so ket, bra, and we call it operator, then by looking on this algebraic construction, we can refocus our attention from this part and this part onto this part and this part. Make sense? So the box to the right is a scalar product that gives 1. The box to the left is ket vector of the scalar. So as a result of applying this operator to the state, we are getting another state. I'm not a good drawer, right? The function, scalar product, getting wave function, quantum state. Make sense? Mm-hmm. So the same idea, maybe in a little more boring notations, is used to describe spins. To flip spin, you have just basis states in the direct product. So now the relaxation stage is over. Now you may want to concentrate. So if we have the state alpha, which we can assume like spin up, and we apply operator that composes of ket and bra, beta and alpha, then what does this operator make to alpha?
Just the operator data.
Converts it to beta. And well, here I think I was thinking that alpha is down. If alpha is down, acting by this operator, it makes it beta, it makes it up. And then since it's flipping up, we can call it S plus, like raising operator. So same idea as coharmonic oscillator. Browsing in the space of eigenstates, but here our space is very restricted. Instead of infinite number of states, we have only lowest and one excited. And by this raising, we go from the lowest to the highest. Right? So S plus and alpha will be beta. And similarly, we can go. You can set up S minus, going from top state to the lowest state. So raising and lowering operators. S plus to the alpha gets beta, S minus to the beta gets alpha. So these states and operators can be expressed as matrices if one needs to. So S plus will be only one here in the amount out of these four numbers. And if our alpha is 1 at the top, beta is 1 at the bottom, then by practicing row by column of such metrics, one flips and makes 1 here and 0 there. And if we use S minus, we need to have 1 in the opposite part, and this matrix is non-symmetric. So here, by practicing row by column for lowering operator, we flip the populated state to the opposite one. So from now on, you do have vision of raising and lowering operators in space of 2 states. Right? Instead of infinite number of states for harmonic oscillator, for spin it's just 2 states, but you have same apparatus of things. So in Dirac notation, this S minus and S plus are just dyadic products. So what, and this little exercise will be of interest, potential interest to Zane and Spencer. So if we multiply raising and lowering operator in matrix form, so just a little exercise. Row by column gives 1, and any other row by columns gives 0. If we swap the order of these two things, then we have another row and another column that gives 1. So by multiplying this flipping operators, raising and lowering operators by each other, we are setting up a diagonal thing, a diagonal projection. Now, let's scroll our memories about what do we remember about harmonic oscillator? What did we get when we were multiplying raising by lowering operator?
1.
It was when we were commuting, when we were subtracting a plus a minus a plus. Then it was 1, correct, absolutely correct. What was the operator like if we do h bar omega a dagger a plus 1/2? Total energy. So by multiplying raising and lowering operator, it gives total energy for harmonic oscillator. When you the constant and multiply. So if we add together this multiplication of raising and lowering operators in different order, S plus, S minus, S minus, S plus, then we will add together these two matrices and it will be identity. 2 by 2 matrix with 1s. If we, instead of factor 1, we put energy of state up and state down in front of here, then this matrix will include energies on the diagonal and it will be Hamiltonian. Right? So by practicing raising and lowering operator, one can express total energy, which is always useful in context of this course. Whew. Forward. So energy of state alpha, energy of state beta, product of raising and lowering, gives Hamiltonian. Why it is important and interesting for Zane and Spencer. If we would have more time and if Zane and Spencer will be here in class, I would definitely invite them to try answering. Now you can just think and maybe write down, and I will declare the answer right away. So, Zane and Spencer are considering Polaronic model and Marcus model when there are more than one potential energy surfaces, depending on electronic state, right? So the kinetic energy for their problems is the same, independent of in which parabola, blue and red. Oh, I do see some chat comment. Where is? Zane answers yes. Oh, okay. Sharing. So, but potential energy is different depending on the electronic state. So we can put the Hamiltonian for Zane and Hamiltonian for Spencer in this way. Kinetic plus potential, but potential is multiplied by such a projector on the state alpha or state beta. And the factor here will be potential energy for ground, U sub G, and potential energy for excited, U sub E. So it will be a mathematical way to formulate this strange situation when there are multiple parameters. So even if the code is written and you are doing practical things, if you want to, Zane and Spencer, if you want to explain your problem to like a professional on the language of Hamiltonian, it's really helpful. So it gives context how to explain this situation of coexisting upper and lower parabolas. So little dictionary, it's our intermediate stage before I dive deeper into spin rotation. So alpha and beta basis vectors, and then four operators. Lowering, raising, product of raising and lowering, inverse product. Okay. I do want to connect these things into the rotating spin. So if I know the state of my spin wave function, the superposition alpha and beta with expansion coefficients, I can practice the bridge between calculations and real world and find observable expectation values. So I just place an operator of my interest in a sandwich between Brian and Cat of the quantum state. If I need population of the upper state, I put S plus S minus inside the sandwich. If I need population or probability that system, the spin or spin-like system in lower state, I just put there S minus S plus. If I need the energy, I put Hamiltonian inside the sandwich. And it is needed in the situations when it is not in the only 100% up or 100% down. It is needed when it is in the superposition of different proportions. So here is the little exercise how to get this population of the state up. So if one practices this thing, opens all brackets, then everything will cancels, and the only thing that will be non-zero is C sub alpha star, C sub alpha without star, which is definition of probability to find system in the state alpha. Yes? Okay. And I understand very much that I'm squeezing material, and if it is not needed, you just forget it. 5 minutes after the lecture. If you need it, you need to reread the recordings, watch the recordings online, or read the book. But so it is projection on state. Now, what if I declare an analogy between spin operators and harmonic operators? So here is the thing that I want to introduce, and here is the thing that we already know. So square root some constant, and then x p, right? With some imaginary unit, and I'll skip the constant. A, some constants, then x and p. Minus, here we plus. Do you remember this statements?
Yes.
Definition of creation and annihilation as addition together of position and momentum. Right? Now, we can assume that there is an analog of position and momentum for spin. And by adding together these analogs of position and momentum, we will get raising and lowering operators. The question is, what are these analogs of position and momentum? And mathematically, by adding and subtracting s plus and s minus, one will literally get them. Okay. Let's keep this stuff, which is cool, but not for today. Okay. Now, two directions of thoughts. First, if one if one makes this linear transformation, adding and subtracting creation and annihilation operator, we will obtain analogs of position and momentum. These analogs of position and momentum for spin will be projections of spin in the direction orthogonal to strongest magnetic field. Basically, it will be projection of spin in direction x and y. If magnetic field makes it to be oriented along z, but there is a chance that it slightly deviates and makes rotations. Now, here I'm going to illustrate the same thing as we did for harmonic oscillator. There, when we needed to find how position and momentum changes over time, we practiced Heisenberg equation of motion, right? We based on your last homework, which is number 7 or 8, you were making commutation between creation operator in Hamiltonian and found that it gives itself. Like A dagger commuting with H will be A dagger, right? And then we were plugging it into Heisenberg equation of motion. We found that operators A and A dagger just rotate in complex plane. One can practice the same trick for the spin operators. One can find how the S plus and S minus operators rotate in complex plane. The equations will be quite similar. So here is equation of motion for creation operator, we need to find commutation between Hamiltonian and this operator. And if one carefully practice it, then one will obtain, so we do h to the s plus and then s plus to h, one will obtain the same operator, but the factor will be energy of state alpha and energy of state beta. And if you subtract these two things, we put operator out of brackets, and inside the brackets, it will be energy difference between the states. And I know that maybe you're falling asleep, and it's really hard to follow. I remember myself being in undergraduate studies, and I start losing track after the first 10 minutes. So the operators class will rotate in complex plane. The quicker, the bigger energy offset between states. It is the same as it was for harmonic oscillator. And as in any quantum problem, the bigger energy offset between states, the quicker is phase accumulation, the quicker is rotation in complex plane. And if one, so h s plus minus s plus h, energy difference s plus. So this operator can be solved, one can solve this as a differential equation and find that s plus as function of t is its initial value, and then accumulating phase with time, imaginary, as energy difference. For the Lorentz operator, S minus, it will be the same thing, but rotating in the opposite direction, right? Now, if we add together, the solution for plus and for minus, which rotate in opposite direction, the difference is only the sign here and there. Then one can practice Euler formula, and by adding or subtracting them, one will get either sine or cosine. So if one carefully expresses S plus as in form of Euler formula, cosine, sine, and then initial value, Euler formula for S minus as cosine, sine, initial value, different sign here, and by adding and subtracting, one will obtain that for summation, the signs will cancel, and for subtraction, cosines will cancel. Same as we did for harmonic oscillator, positional harmonic. And as the result, one will obtain this solution. So Sx, which is a summation of creation and annihilation, will rotate according to its initial value as cosine, and the y projection will rotate as its initial value as sine. And there could be a little component, like if at the initial point of time both of them are non-zero, then it will be a little bit of sine and a little bit of cosine in this rotation. But the direction of rotation will be the same, like counterclockwise. And this calculation will bring us to the store of magnetization. So if the x projection of spin and Y projection of spin changes simultaneously to draw a circle, then magnetization, which is proportional to projection of spin, will also make a circle. And in nuclear magnetic resonance experiment, it is basically what one does. One excites these nuclear spins with radio frequency electromagnetic radiation, then stops exciting and watches for the system keeping this rotation of magnetization, irradiating radio frequency back. Due to homogeneous, inhomogeneous broadening, it dephases, but after some time, one looks how this responds on different frequencies. So one is looking for this rotations of magnetization. So it is 50 minutes, and I did arrive to the slide. So I think we have completed everything. Thank you much for your patience. Send me an email if you need to talk about the project.